Hi there, this is the last part of section 6.2 and hopefully the shortest. Let's see, a linear transformation is 1 to 1 if and only if the kernel of T contains only the zero vector, which means a 3 by 3 matrix transformation would reduce to the identity, and then you would get a unique solution of xyz equals 0. So that would be equivalent to the kernel, to the set of all vectors that go to the zero vector to be only the zero vector. A linear transformation is onto if the rank of the transformation is equal to the dimension of the domain. So we're going to see examples for what that means. T is called, so there's a theorem, so these are all three theorems in your book in section 6.2. If we had a 3-hour class, I would do proofs of all of them. But right now, we're speeding things along and we're just trying to understand what's going on with them. If you have a linear transformation in which the dimension of the domain and the dimension of the range are the codomain. So W is the codomain, V is the domain. So if you have a transformation in which the dimension of the domain is the same as the dimension of the codomain, that would be a square matrix, a 3 by 3 matrix, a 2 by 2 matrix, 4 by 4 matrix. Then the condition of 1 to 1 and onto are equivalent. So the matrix can only be 1 to 1 if it's onto and the other way around. So things are a little bit simplified for square matrices there. And finally, the reason why we cover this section at all, a linear transformation that is 1 to 1 and onto is called an isomorphism. So this is a function, right, that takes, a linear transformation would be a function that takes each element of V to its own element in W, and it's 1 to 1 and onto. Then you can, it's called that we created an isomorphism between the two spaces. We can create isomorphism, we can come up with functions that takes each element of R3 to an element of the coefficients of polynomials in P2 by, let's say, you take vectors like A, B, C, and you assign them the polynomial x squared plus bx plus c. Here, this is a linear transformation that takes each vector in R3 to a polynomial in P2, and we can show in the next section in 6.3 we're going to be able to create a matrix that gives this transformation, and then we'll show that that matrix is 1 to 1 and onto. So you can show that the following are isomorphic spaces. So that's just an example. R3, P2, this space that seems to be embedded in R4 but has only 3 components really. So that's like a projection onto the 3 space. And the set of matrices that are 3 by 1. So, you know, column matrices. So let's see an example here. Suppose that you have a transformation that's given by left multiplication by this matrix. That means in order to find, let's see, and we want to find the nullity, the rank, and determine if it's 1 to 1 and onto. So to determine the nullity of this matrix, what we did in the past, we wanted to see the nullity is the dimension of the solution space. So let's see, what kind of vectors would we multiply this matrix by on the left? These would be your input vectors, and they would give you the dimension of the domain. So you would need to multiply this by a two-dimensional vector, right? Because this is 3 by 2 and it needs a 2 by something to be multiplied by. And to determine the nullity, we would want to get a three-dimensional zero vector, right? So the solution space of this equation. So we would have 0, 0, 0 here. So now I have a 3 by 1 matrix. All right, so we determined that the dimension of the domain is 2 and the dimension of the codomain is 3 by just analyzing the dimensions that work here. So this so the bottom row gives you nothing, 0 equals 0. The second row gives you that y equals 0. And the top row tells you that x plus 2y equals 0, and so x equals 0. So this system has a unique solution. That means 0 is the only solution to this equation. And so the nullity of t is equal to 1 because it's equal to 0, I'm sorry. The kernel of t only contains the 0 vector. That means that's the same as saying the nullity is equal to 0. If the nullity was 1, you'd have one parameter here in the solution, but you don't need any parameters. So because the only solution to this equation is the 0 vector, this means the kernel of t is equal to only the 0 vector. So only the 0 vector gets sent to this three-dimensional 0, 0, 0. So the nullity is 0. What is the rank of t? Well, it has two leading ones in row-reduced form. So the rank of t is 2. Is this 1 to 1? Yes. Because the nullity is 0, because the kernel is only equal to the 0 vector, this is 1 to 1. Is this onto? Well, let's see. In order for it to be onto, the rank of t, which is 2, needs to be equal to the dimension of w. This here is w. The dimension of w in this particular example is 3. So the codomain is three-dimensional. Because these two do not equal, we say that it's not onto. Because it is not onto, it is not an isomorphism. So in order for this transformation to be an isomorphism, it needs to be 1 to 1 and onto. Not onto means not an isomorphism. Awesome. So that's done. Let's see. This problem, it would take, to determine nullity, it would take three-dimensional vectors. So the domain Rn is R3, and you would get vectors in R2. So for this, we'd get x equals, xyz, sorry. You'd get x equals 0, y equals 0, and z would be a parameter. So you would let z equal to t and have it parameterized that way. Because it has one parameter, the dimension of the kernel, or the nullity, is 1. So the nullity of t is 1, which is not equal 0, which means, so the nullity is 1, it is not 1 to 1. So let's see, we cannot apply this theorem that says if the dimension of v and w are the same, then 1 to 1 is the same as onto, because this is not a square matrix. the dimension of V is 3, the dimension of W is 2. So now we have to figure out if it's onto. The rank of this matrix is 2. And that is equal to the dimension of W, or the codomain. So that means yes, it's onto. Because it is not one-to-one, it's not an isomorphism. So it has to be both one-to-one and onto to be an isomorphism. So finally, this matrix would take vectors from R3 and it would put them onto R3, into R3. So let's see, if you reduce this matrix, it reduces to the identity, which means it has a unique solution, which means the kernel of T only contains the 0 vector. This only has the solution of x equals 0, y equals 0, z equals 0. Buckley, come here. So that makes this 1-to-1. Hey baby, come here. Now, again, if you reduce this, come here, be a good boy. If you reduce this, you see that the rank of T is 3, and that is equal to the dimension of W. That makes this onto. Because it is both 1-to-1 and onto, this transformation is an isomorphism. Now, let's see if you can go and do that and go to student.desmos.com and enter this code. You'll be able to do an activity for 6.2 and see if you figured out what I explained to you here.